Hello and welcome to the notes for section 10.3 hyperbolas. We are familiar with hyperbolas, but what we see here, seems a little bit strange because it doesn't look like it's a function. It would not pass the vertical line test. In this section we focus on the geometric properties of hyperbolas, and it doesn't matter if it's a function or not. We care about the geometry behind hyperbolas. So what's the geometric definition of a hyperbola? I'll read it first and then I'll explain a little bit more what it means. A hyperbola is the set of all points, the difference of whose distances from two distinct fixed points is constant. These two fixed points are the foci, one focus and another focus. So what does it mean? If we have 2 points F here and there, we look at all the points in the plane who have the following property. From the focus to a point on the hyperbola, if we look at this distance and we subtract that distance, then it's a constant number. So I don't know what it is in this case, but d2 minus d1 would be the same for every point on this hyperbola. For example, d2 minus d1. That remains constant. There are lots of words, there's lots of vocabulary for hyperbolas. Here's a summary. A hyperbola has 2 branches here and there. This hyperbola opens left and right, we say. There's also hyperbolas that open up and down. The vertices are the 2 points on each branch that are closest to each other. Then we have this point here, which is the focus, and another focus there, so the focus is not part of the hyperbola. And between them we have the center. The center is the midpoint of the vertices, it's also the midpoint of the foci. All these 5 points are on a line, and this line is called the transverse axis. In this case, the transverse axis is horizontal. Finally, the distance between the center and the vertex is A. The distance between the center and a focus is C. There's also a B value that we'll see later, but it's not very meaningful to look at it geometrically. There are 2 standard equations for hyperbola. It depends on the transverse axis. If it's horizontal, like the example below, this is the equation. If the transverse axis is vertical, that is the equation. Here is a hyperbola with a transverse axis that is vertical. So you can see the focus is here, vertex, center, vertex, focus. It's vertical. How do we see the difference with the equations? Well, in terms of x and y, it's the x term minus the y term equals 1. In the second case, it's y term minus x term equals 1. This is how you distinguish between these 2 cases. Be careful when you learn about section 10.2 ellipses. How to differentiate between the 2 cases is completely different, so don't confuse that. A, B, and C are related differently for hyperbolas and for ellipses. This is also something you have to be careful. In both cases we have A and B and C that are related with a Pythagorean identity, Pythagorean relation, but it's not the same one, so be careful. In the case of hyperbola, it's a squared plus b squared equals c squared. Hyperbolas have asymptotes. In this example, we can see one asymptote is here, and the other asymptote is there. The concept of asymptote is exactly the same as what we've seen. The hyperbola is actually approaching the asymptote more and more as it goes toward infinity. These 2 asymptotes intersect at the center. So this is what is written here. Each hyperbola has 2 asymptotes that intersect at the center of the hyperbola. The equations of the asymptotes are given below, right here. There are two cases again, if the transverse axis is horizontal or vertical. In each case, there are two asymptotes. So if the transverse axis is horizontal, like in this example, there's still two asymptotes. These two asymptotes are found by choosing plus and choosing minus. Y equals k plus b over a times x minus h. Y equals k minus b over a times x minus h. So when we solve exercises, we will always find ourselves in one of two situations. Either you are given the equation of the hyperbola, you have to find HKABC in order to answer the question. This is like an intermediate step. So the information may be what are the vertices, what are the equations of the asymptotes, etc. So you have the equation. First you need to find HKABC, and from there you can find the information that you are asked to find. The other case scenario is the same but backwards. You are given informations about the hyperbola, and with this information provided, you need to find the equation of the hyperbola. And to do that, you need to find the intermediate step, which is HKABC. So let's see in this exercise. Find the standard form of the equation of the hyperbola with foci at -1, 2 and 5, 2 and vertices at 0, 2 and 4, 2. So here obviously we're given the coordinates of the foci and vertices, and the question is, what is the equation? We will always be using the table that you can find at the end of the notes for this section. It has this table. You will have that in the quiz and test, except for this line. This line will be erased, and the asymptote line will be erased. So you will need to know that, and maybe just fill it in quickly at the beginning of a quiz. Everything else will be given. Okay, so we have the foci. We can represent them on a plane. Here's -1, 2. Here's the other foci, 5, 2. The vertices are at 0, 2 and 4, 2. And the center is the midpoint of the vertices. It's also the midpoint of the foci. So it's very easy to figure out that the center is at the point 2, 2. That's great because the center, as you can read, is HK. In both of these cases, it's HK. What you need to find, and we should have started with that, is to decide whether we have to work with the first column or whether we have to work with the second column. Well, clearly here we have a horizontal axis. So that means the hyperbola is going to be opening left and right. So now that we know that, the shape is opens left and right, we know that we are working with the first column. So the center is HK, as I said. We know that our center is 2, 2, and therefore H equals 2, K equals 2. We saw earlier that the distance between the center and a vertex is A, so we can find A equals 2. And the distance between the center and one focus is 3. So we can find, it's C, so we can find C equals 3. If you couldn't remember that from the sketch earlier, just look at the first column. Our center is HK. The foci are H plus C, K. So clearly the difference is C. What about vertices? H plus A, K. So there's a difference of A compared to the center. So the distance is A with the vertex, it's C with the focus. We have A and C. We can use the Pythagorean relation a squared plus b squared equals c squared, plug in the values of a and c, and find b equal root 5. Therefore, now that we have a, b, c, h, and k, we can look at the standard equation, plug in all these values, and the answer is x minus 2 squared over 4 minus y minus 2 squared over 5 equals 1. In the next exercise, we have the equation of a hyperbola, and we want to find the equation of its asymptotes. So you can notice that 4x squared minus 3y squared plus 8x plus 16 equals 0 does not look at all like the standard form. So the first thing we need to do is to write this in standard form. To do that, we use completing the square. The x terms are 4x squared plus 8x. I'm going to put them together and factorize the 4. 4x squared plus 4 times 2x. I'll do the same with the y terms, and here luckily there's no y, there's only a y squared, so it's going to be very easy to create a square. Let's focus on the x term first. We'll just read this part vertically. So 4 times x squared plus 2x, I need to complete the square. You really need to know how to do that in every single one of these 3 sections that we're doing about conics. You need to complete the square sometimes. It's x squared plus 2x plus 1 minus 1. And by adding this plus 1, I can form a square x plus 1 squared. The minus 1 is left over, so here it's still here. I don't want this minus 1 in parentheses, so I'm going to distribute the 4 to get rid of the parentheses. 4 times x plus 1 squared minus 4. Here it is. What about the y terms? Well, y squared is simply y minus 0 squared. You don't need to write that really, but it's nice to do it this time so that we can see k equals 0. And we have a constant term of 16 that we're going to move to the other side, and the negative 4 that we have here is also going to be moved to the other side. So this equation has now become 4 times x plus 1 squared minus 3 times y minus 0 squared equals negative 12. The equation in standard form is always equal to 1. So here, because of this negative 12, I need to divide by negative 12, and I have reached now negative x plus 1 squared over 3 plus y minus 0 squared over 4 equals 1. Notice how in the standard form it's always the first term minus the second term. Same here, first term minus second term. So we just rearrange this equation here like that. It's y squared over 4 minus this term equals 1. This is how you can find whether you are in the first column or the second column. Now that we see it's the y term minus the x term, it's this case here. We are in this column here. This way of figuring out which column we are working with is different in section 10.2. So when you learn about ellipses, be careful, there's a difference here. Alright, so now we can find the equations of the ellipses, of the asymptotes, sorry, by finding a, b, c, h, and k. A is equal to 2 because it's y minus k squared over a squared, and b is equal to root 3. H is equal to negative 1, x minus h, and k is equal to 0, y minus 0. Now that I have a, b, h, k, I actually this time don't need the c at all because the asymptotes don't require c. I can simply write that the asymptotes are y equals 2 over 3, x plus 1 plus 0, and y equals negative 2 over 3, x plus 1 plus 0. Obviously, I don't need to write this plus 0, but I wanted to just to show the plus k. Okay, how can we find the equation of the hyperbola who has vertices at 3, negative 2 plus or minus 3, and with these two asymptotes? The center is the midpoint of the vertices again, so the center is going to be 3, negative 2, which yields the value for h and k. Also, a is the distance between the center and the vertices, so a is equal to 3. So we can already sketch the situation. We have the center here, and we have one vertex here just above the x-axis, and we have another vertex down there. There are two asymptotes that I drew in orange here, like that, and the asymptotes are 2x minus 8 and negative 2x plus 4. This general form of the asymptote is plus or minus a over b x minus h plus k. How do I know which column I'm working with? Well, because of this sketch, I've realized that the transverse axis is vertical. I've therefore realized that the hyperbola opens up and down, so up and down I must be in this column. The asymptotes have a slope of a over b. In this case, we know that the asymptotes are 2x minus 8 and negative 2x plus 4. So a over b has to be equal to 2. Since we know that a equals 3, 3 over b has to be equal to 2. And that's how I find b to be 3 over 2. So I have h, k, a, and b. Once again, I don't need to find c. Most of the time I do, but in these two examples I don't. I can just write the answer: y plus 2 squared over 3 squared minus x minus 3 squared over 3 over 2 squared equals 1. And that's my answer. The last part of this section is about classifying conics, so it's kind of a overall view of sections 10.1, 10.2, and 10.3. The general equations of conics is given by this long equation. There are terms in x squared, terms in y squared, terms in x, terms in y, and constant. There are, in what we've seen this year, there's never going to be a term in xy. So b is always equal to 0. b equals 0. If a equals c, then it's a circle. If a times c equals 0, which basically means if a equals 0 or c equals 0, then the conic is a parabola. If a times c is greater than 0, we are dealing with an ellipse, and if a times c is less than 0, it's a hyperbola. So let's have a look at two simple examples. 4x squared minus 9x plus y minus 5 equals 0. There's no c. There's no terms in y squared, so obviously a times c equals 0. I shouldn't say there's no c. I should say c equals 0. A times c equals 0, but a is not equal to c. So a times c equals 0. We're not in a situation where a equals c. It's a parabola. What about this example here? A equals 2, c equals 2, so a equals c. It's a circle. There's various applications to the geometric property of hyperbolas, GPS, nuclear reactor shapes, etc. Also, comets entering the solar system follow a path that is a hyperbola. And if it does, the sun is at one of the foci. At the bottom of that, you can find this table with all the information, and that is all for this section. Thank you.